Okay, so today, I should remind you, if you have regrades, please get them in by Wednesday. And I think we're going to be fairly stringent about that deadline. So if you've got regrades, make sure you get those in. Okay, so today we are going to return to the subject of programming with shared memory, which you're all pretty familiar with. And the topic will be how we make programming with synchronization easier using a concept called transactional memory, which is pretty interesting. And so let me introduce the topic by talking about what you already know, right? So we've talked about synchronization primitives, low-level synchronization primitives, and we said that the key hardware mechanism you need to implement synchronization is an atomic load and store, right? And these come in a variety of different types, right? You could have fetch and op, test and set, compare and swap, and then we said that on modern systems, they actually break these into two different memory operations, load, linked, and store conditional, and the coherence system connects them together and makes them atomic. All right, so the key thing you need to implement synchronization primitives is an atomic load and store, right? And so once you've got this in your hardware, then you can implement various different kinds of atomic operations, synchronization operations like locks and barriers. And of course, with locks, you can implement lock-free data structures. However, programming with these, admittedly higher level synchronization primitives is still pretty difficult, right? So we've seen that, it's actually pretty challenging to develop lock-free data structures. If you're not careful and you do the wrong synchronization order, you end up with deadlock. And so the question is sort of, are there better ways of dealing with synchronization? And in particular, can you raise the level of abstraction and make it easier for programmers to get both correct programs and high performance programs, which is what we're all after, right? Okay, so the idea then is we're going to talk about transactions. We're going to talk about the fundamental programmer's view of transactions, which is really basically pretty simple. And then we're going to talk about how, transactions differ from synchronization primitives like lock and unlock. And then once we kind of understand why you'd want to use transactions and how you'd use transactions, then we want to talk about how you implement transactions. And they're both software and hardware ways of implementing transactions with different performance characteristics. And so we'll talk about that. But before we talk about the details, we'll also talk about some of the basic design space trade-offs that you have for implementing transactions, dealing with how you deal with the different versions that get created with transactions, how you detect whether there are conflicts between transactions, and the granularity of detection, right? So, and this will kind of, remind you of our discussion of cache coherence. And when we talk about cache coherence, we talked about two levels at which you could do detection, right? We spent a lot of time talking about doing detection at the level of cache lines. And what was the problem with doing things at the level of cache lines? Something that, of course, you revisited on the midterm. What happens? Yeah. You get false sharing, right? So what if you do the granularity of detection at like the operating system page level? False sharing gets much, much worse, right? So we'll see this notion of granularity of detection rear its ugly head again as we talk about transactions. Okay, so first of all, why is locking, as we've currently discussed it, difficult, right? The fundamental problem is this trade-off that the programmer has to make between having a correct program, which is what we all want, and having a high-performance program, which is also what we want, right? I mean, the purpose of taking, this course, parallel programming, is to develop high-performance programs, right? So there's this fundamental trade-off that one has to deal with, and this comes down to sort of the granularity at which you do the locking, right? So if you do it at a coarse grain, then you get a low degree of concurrency, right? So you imagine, right, when we're talking about locking data structures, you can have a lock around the whole data structure, right? Or even worse, you can imagine that I have a lock on all of shared memory. So every time I touch shared memory, I have to grab a lock, and that means that only one thread can be touching shared memory at any one time. So this is low concurrency, right? And so, of course, the opposite extreme is to go to some sort of fine-grained locking scheme, right? And this can, have much higher concurrency because now many threads could potentially be touching the same data structure if you've got fine-grained locking. However, the problem here is now you open yourself up to the potential for problems with correctness, right? So deadlock, racism, and such, right? So the question then is sort of, is there a better way of thinking about or implementing synchronization? And that is the reason for transactions, right? So let's look at sort of an example. So suppose I want to make a deposit into your account, right? So the first thing I need to do is to get your account balance, and then I need to increment the account balance by the amount of money being deposited, right? So first I do a get from your account, and then I increment the balance, and I put that back in your account. Well, you'd be pretty annoyed if in the middle of the get, somebody else wanted to give you some money, right? And so they got the wrong amount because you didn't have synchronization, right? So the way to fix that is to make the deposit method atomic by using locks, right? And so you put locks around, you take an account lock, and so if you do this, right, then you're going to ensure that the deposit method is atomic. However, you could, instead, if you were using transactions, you would just wrap the atomic construct around the whole of the contents of the deposit method, and you're declaring to the system that you want this sequence of statements to be atomic, right? So the thing to take note of is that atomic is declarative. You're saying what you want the system behavior to be, and you don't have to explicitly talk about how it's actually implemented, right? So once you declare atomic, then it's up to the system to implement atomic in the right way, right? So in fact, under the covers, atomic could be implemented with locks, but you as the programmer don't see the locks. Your interface is this atomic declaration, right? And then, of course, how exactly it gets implemented and how you make sure that you get good performance is the subject of the rest of the lecture, right? But it's important to note that atomic is this declarative abstraction, right? You say what you want, not how to get it, right? And we've seen this in the past, right? So we've talked about declarative abstractions in which you say execute these independent 1,000 tasks, right? So what's an example of a declarative abstraction that we've talked about in this class?
Like a bulk launch of ISPC tasks.
Yes, so an ISPC for each, for example. That's exactly correct, as opposed to an imperative abstraction where you say explicitly how you want the behavior to work. So you want to say, for example, instead of saying, launch a bunch of independent tasks, you say spawn n worker threads, assign threads to work explicitly using some sort of shared task queue, right? So the synchronization analog to declarative versus imperative semantics are, transaction says perform this set of operations atomically, whereas if you are dealing with locking, then you have to explicitly acquire locks, perform the operations, and release the locks. And so the abstraction is much lower level, and it's imperative. It says what to do as opposed to, it says how to do it as opposed to what to do, right? So imperative is how, and declarative is what? Okay, any questions at this point? Okay, so let's talk about what sorts of semantics you have with transactions, right? So we're talking about transactional memory, which is inspired by database transactions. How many people here have taken a database class? Good, a fair number of you, right? So in databases, you hear about ACID properties, right? So we have similar semantics for transactional memory. So you've got an isolated sequence of memory accesses, right? So the first key thing that you want in your transactions is atomicity, right? It means all or nothing. Either all of the reads and writes inside the transaction take effect, and in particular the writes change the state of the memory system, or it's as if none of them occurred at all, right? So you can imagine it's all or nothing, and that means that you have this atomicity property. The second property of transactions is this notion of isolation. The fact that within a transaction, any of the reads, or in particular the writes that are made by the transaction, cannot be observed by any other transactions in the system. Okay, so the operations within a transaction are completely isolated, right? And then lastly, the last property is serializability, which says that, hey, the order, I can have a serialized order of the execution of each of the transactions in the system, right? So I can order all the transactions in the system in a serial order. However, the exact order is not specified by the programmer, right? That's left up to the system. But there is a serializable order that we can impose. The system will be imposed on the order in which the transactions commit. Okay? So we've got atomicity, isolation, and serializability. We don't really have durability because, of course, memory can fail, right? So that's the D is missing in the semantics or the properties of transactional memory. So the way to think about transactional memory then is a transaction is a sequence of reads and writes on various addresses that are both isolated and atomic, right? So you can think about the operations that are made within the transaction as being the same as as a single operation that we talked about in the context of cache coherency, right? So that each of the transactions then can be thought of as a single atomic memory operation that occurs, and that can be serialized by the system, right? So with this in mind then, what consistency model do we have for transactional memory? What consistency model does transactional memory give you? Yeah.
Sequential consistency.
It gives you basically sequential consistency. So you can imagine, right, that, with that picture where the pointer points from one thread to the next in some random order, but in this case, every time it points to a particular thread, it takes a whole transaction's worth of memory references, right? So it is essentially sequential consistency. Some people have called this transactional consistency to differentiate it from the fact that you've got this bulk operation of memory references as opposed to a single memory reference that gets selected each time. But essentially it is sequential consistency. Question?
Transaction, is it ever possible to read and write the same variable? Or would that mess up?
Read and write, so you can do whatever you want inside the single transaction because it's isolated, right?
So it doesn't matter, for example, the order in which I read X, Y, Z within that single transaction.
Well, you've got to match the whatever was stated in the program order, right? Yeah, you can't mess that up, right? In particular, the dependencies in the program order, right? If there are no dependencies, then of course you can reorder things. If there are, you've got to respect them, right? Yeah. Okay, so we basically have sequential consistency. So let's motivate a little bit more why you want transactional memory, right? So this is a Java hash map, right? So we used to run this class in Java. Many of you, how many people actually know Java here? Good, all right, good. So here's a Java hash map, right? And it maps a key to a value. You can look at the code. It's fairly straightforward. You get a hash bucket and then you find the element within the bucket. But of course, if you want to use this in a multi-threaded parallel context, it's not thread safe, right? So it's not thread safe, and so of course it doesn't have any extra overhead for locking, but it'd be a bad idea to use this in a threaded environment, right? So if you want to use it in a threaded environment, what you want is some sort of synchronized map, which is what Java 1.4 gives you. So it essentially uses synchronized, which is a way for specifying that this method you need to take a lock before you use it, right? However, you don't have to explicitly release the lock, but you do need to, so the system does the acquisition for you. Okay? So synchronized, it's easy. You make the whole hash map synchronized, and now it's thread safe, so you can use it within a threaded environment. However, the performance of this hash map may not be that good because you've got this single lock which locks the whole data structure, right? Okay, so what should we do to potentially improve the performance of the Java hash map? What can we do? Yeah.
Linked list to each bucket instead of a lock to the entire.
Right. So we can do a lock per bucket as opposed to a lock over the whole hash map, and this would potentially give us more concurrency and more performance. All right. So now with this finer grained locking, it's potentially thread safe, but the problem is that now it's more complicated to implement, right? So it's much more complicated than just putting a synchronize around the whole method. Now you've got to dig into the details of the implementation of the hash map. Okay? So in terms of performance, things are going to look a lot better, right? So in this case, where we're looking at the execution time, so lower is better from 1 to 16 processes. And so the synchronized, the whole hash map doesn't really improve much, right? So you see performance roughly doesn't improve with parallelization because you don't have enough concurrency. However, with fine-grained locks, we do see this improvement in performance as we increase the number of processes. So this is all good, right? So thumbs up for fine-grained locking because it's always a win. Is it always a win? What's happening here? So in this case, the coarse-grained locks, give you this no concurrency line, right, which doesn't improve with number of processes. But what is happening with fine-grained locks? So we're going from a hash table here now to a balanced tree data structure, and now we are using fine-grained locks with the balanced tree. So why at one processor do we have the execution time being so much worse than the coarse-grained locking scheme? Yeah.
The ratio of work you do for lock and unlock on the tree, where compared to what you're doing with the hash table, where you're iterating over a linked list for lock unlock.
Right. So you've got to take if you do potentially doing hand-over-hand locking, you've got to take a lot of locks for very little work, and so you have a lot of overhead associated with the fine-grained locks, and it takes you 4 processes worth of capability in order to overcome the overheads of the fine-grained locks, right? So this is not so great. I mean, it does scale, but there's a lot of overhead that you have to overcome, right? So the question is, could you do better? And so with an atomic construct, right, you just use atomic and say that you want the method to be atomic, and thought there's seem to be missing. It's coming later. Coming later. All right. So the idea is that with atomic, I just specify that the whole hash map operation is going to be atomic. So now it's good in that it's thread safe. It's just as easy as kind of locking the whole method with synchronized. And the question is, will I get good performance? So let's look at the performance of a transactional system in the context of a tree update by 2 threads, right? So in this case, we've got a tree, and we want to modify nodes 3 and 4 in a thread-safe way, right? And so let's assume that we're going to use fine-grained locking. So we're going to do some hand-over-hand locking, and so we need to lock the path to node 3. And so the red path is the path to node 3, and the yellow path is the path from the root to node 4. And since it goes through nodes 1 and 2, both paths go through nodes 1 and 2, you potentially have a case where the update of node 3 delays the update of node 4, right? Does everybody see that? Okay. Now, the question is, should there actually be a case where we can actually update nodes 3 and 4 at the same time? They're independent, right? So potentially we should be able to do this, right? And so with transactions, you can actually make that happen, right? So the way to think about transactions then is that there's some state that you read during the transaction, right, called the read state, and there's state that you write during the transaction called the write state, right? So the read state for transaction A is nodes 1, 2, and 3, right? And what's the write state? 3, right? So 3 is the write state. And then for transaction B, which is going to update node 4, the read state is 1, 2, and 4, and the write state is 4, right? And so what we're trying to figure out is whether the transactions conflict, and they will conflict if there is an intersection between the read and the write states of the 2 transactions, right? And so in this case, there is no intersection, and also in that case, there's no intersection, and so there's no read-write or write-write conflict, and so these transactions can both operate concurrently, and they do not conflict. Yes?
I think going back to what I was trying to ask earlier was, in this case, there's of course no conflict, but in a case where 2 parallel, threads or whatever are writing the transaction A and B, and they're both writing the tree, what would the behavior of the transaction in that case, given that there would be a conflict?
Okay, what do you think it should be?
I guess one of them is given priority over the other.
Right, you've got to serialize those transactions because there would be a conflict if you didn't.
So does the other one get flushed, or does it still end up writing?
Well, it's eventually got to execute, right? And the question is how we manage the operation of the transactions. We're going to get to that. But from the point of view of the abstraction, those transactions will be serialized, right? Okay, so in this case, there is no read-write or write-write conflict. But in the case, that you just brought up, they both are trying to, both the transactions are trying to update node 3. Now there is a conflict, and so we need to serialize them, right? Okay, so this is the graph that I thought was going to come earlier, right? But we're just showing that, okay, now you have transactions with the right support. You're going to get good performance in as good as fine-grained locking with transactions. That's the yellow line, which is labeled TCC, which is a transactional memory system that has hardware support, and that also, even the case where you didn't do well with fine-grained locks, you'll do well with transactions, again, with the right sort of hardware support. So this is the motivation for transactions, the idea that you can get an easy-to-use programming model coupled with high performance because you get to get the performance benefit of fine-grained concurrency, right? So transactions will only conflict when they will only be serialized when there are conflicts. Yeah.
Just to confirm, the job of figuring out what data is in the read state and what's in the write state.
We're going to get to that. This is just the abstraction, and we can talk about the details. Believe me. Hold on, it's coming. All right, so back to the abstraction here. So we've got this doubly linked list, and we want to we've got this push left method, and we want to make it thread safe with transactions. So the question is, how should we do that? So I'll give you a couple of minutes to look at the code, and you can consult with your neighbor, and then we'll ask for a solution for how we make this code thread safe with transactions. As soon as somebody has a solution, let me know. Yeah.
All the lines below the QN val equals val.
That's correct, right? So just make all of the operations on the variables associated with the doubly linked atomic, and then you go, right? None of the tricky hand-over-hand locking and figuring out what's what. You just say, hey, I want all this stuff to be atomic, and system, make sure that you do as you're told, right? Okay, so everybody get that, the idea that it's fundamentally easier to program with transactions. Another benefit of transactions is what happens when failure occurs, right? So how do you deal with failure atomicity, right? In the case of locking, you've got to remember to, in your exception handler, release any locks that you've acquired and clean up things in the right way and restore memory or the state of the system to the way it was before the method executed. And this is much easier with transactions because essentially when you abort a transaction, it's like a big undo, right? So you get the state of the system back to the point at which you started executing the transaction. Great, right? You don't have to worry about figuring out what state you need to put back. You don't have to worry about releasing any locks that you've acquired. And so it's a very clean and easy way of recovering from exceptions. So, failure atomicity with instructions, right? So if you're trying to do a transfer and it fails, you can the transactional memory system will guarantee that any memory updates are undone, and you don't have any locks that you have acquired that are lying around potentially causing deadlock. Okay, a really important idea in sort of software development is the idea that you should compose smaller modules together to build bigger, more complex software systems, right? And so you want composability in your system in order to make sure that you can kind of build complex software from simple components. But the problem is that with locks, this idea of composability breaks down. Look at this example, right? So we want to do a transfer from account A to account B. And so, what we're going to do is we're going to use a nested synchronized in which we get a synchronized, essentially take a lock on account A followed by a lock on account B, right? So this is fine. So if we call transfer from A to B on thread 0 and transfer from B to A on thread 1, what happens? Well, we get deadlock, right? We thread 1 first gets a lock on A, and thread 2 gets a lock on B, and now we're in a deadlock, the deadly embrace situation, right? So how do we fix this? So what's the solution to not having deadlock in this situation? Yeah. That's one solution. What if I don't give you transactional memory, I only give you locks? Yeah.
Could you synchronize withdraw from A and synchronize B?
Synchronize A. No, but you want this to be atomic, right? Yeah.
And you always have to synchronize in the same order.
Right. So you need to order the lock acquisition by some global order, right? So maybe you could use always synchronize a lower numbered lock before a higher numbered lock, right? So you need some global mechanism, but this global mechanism breaks composability, right? Because now you need to know globally what to do in order to compose these simpler components together, right? And so this system-wide policy, breaks software modularity, and so what you want then is transactions, right? So you want to wrap an atomic around the withdraw and deposit. But as we've already seen, there are atomics inside withdraw and inside deposit, right? And so now you've got nested atomics. But nested atomics, how should nested atomics work, right? If I told you nested atomics, what would you assume about the outer atomic? Yeah. Can you be more explicit?
Just like there's not going to be, if you have an outer atomic, there's not going to be multiple people looking inside that.
Right. It subsumes what happens in the inner atomics, right? So the outer atomic takes precedence, and you assume that everything within the outer atomic is going to be atomic, right? Good. All right. So now you declare your intent with this atomic, and then the system will implement things and manage concurrency. And if it turns out that you have no concurrency, as in this first transfer between accounts A and B, then the atomic regions will be serialized, right? But in the second example, where we're transferring between A and B in one transfer and C and D, account C and D in the second transfer, now we get concurrency, and the system should allow that and provide the performance benefit. Yeah?
Just to clarify, for the second example of concurrency, you wouldn't put it in an atomic, right? Because if you put it
Why would you not want to put it in atomic?
Because, like you just said, if you have like a larger scale atomic, only one thing can happen at a time. Or
No. Go back to the example of the tree.
Oh, I see.
in this case, is there a conflict between this transaction and this transaction?
No.
No conflict. Therefore, they should be able to run concurrently, right?
And that's regardless of if we specify the atomic or not.
No, you are inside a transaction. Both of them are inside. They're two transactions. They're executing at the same time. They're executing at the same time. And the question is, do they conflict? Yes, then we serialize them. No, then they should get to run concurrently. Right? So in this case, we serialize the two transactions or the two transfers in this example. And in this case, we allow them to run concurrently. It's important that you get that. Other questions? All right, so we have this, that's the key benefit of transactions, the fact that you do allow this concurrency if there are no conflicts. All right, so, just to recap now then about transactional memory and why we want to use a construct, right? So first of all, we've got this notion of it's an easy to use synchronization construct, right? So, we said it's difficult for programmers to get synchronization right. You're stuck between optimizing performance with fine-grained locking or getting correctness with coarse-grained locking. And so the idea is that transactions are as easy to use as coarse-grained locks, but potentially could give you the performance of fine-grained locking. Okay? And so, the idea is, instead of you, the programmer, having to worry about how to implement the details of a fine-grained locking scheme on a complex data structure, such as a tree or a doubly linked list, you let the system do the work for you and give you high performance. And then this notion of failure atomicity in recovery, this idea that you can recover simply by aborting the transaction and letting the system recover the data and worry and not have to worry about releasing locks that you've acquired. And lastly, a very important point is the fact that transactions compose, right? And so you can compose simpler modular components together to form more complex software systems and not have to worry about a global locking scheme. Yeah.
Well, why is it that you can only obtain most of the benefit? Like, is this not optimal?
Well, the question is that in certain cases you may be able to do something that's you may know something about the data structure, which means that by just looking at the read and write state, you could do something a little more optimized, right? And that's because you know something about the data structure, right? So if I just look at read and write state, I might say that these things can conflict, but you may know that something else that says, hey, they really don't conflict, and that in fact you could get concurrency here, right? So, yeah, I mean, it's usually extra knowledge that you bring to the implementation that would allow you to do better in the case of a pure transactional memory system. That's yeah.
Fine-grained locks also just do better in some cases. Like, if you put atomic on something that's they're always gonna have to be serialized, but a fine-grained lock, part of that would actually be concurrent?
Yeah, maybe. Yeah. Again, you might be able to get finer granularity than you can with a transaction. Yeah. Okay. So it's important to understand that sort of there is this difference between atomic and locking. They're not the same, right? So atomic is this declarative construct saying, here is the behavior I expect of the atomic region, and locks are a way of implementing synchronization, right? And locks can be used for purposes beyond atomicity. And just because you have atomic doesn't mean that all your problems are solved. You could still use atomic incorrectly, and these are called atomicity violations. And in certain cases, atomic simply won't work. All right? So here's the example. Right, so What about replacing synchronized with atomic in this example? Will this work? So I replace synchronized with atomic.
Conflicts, right?
Yeah, go ahead.
Oh, sorry.
No, yeah, it's conflicts, like you said. It's will be serialized, but one has like an infinite loop that's waiting for the very end.
Yeah. Fundamentally, what are the semantics of atomic?
If there are conflicts, it's going to see the flag in, like if you have a light here, and you have
If I gave you this code, given that I've told you about the semantics of atomic, what would you expect to happen? Yeah.
The two blocks need to be scheduled in a serializable manner, and this code relies on kind of the flag set being interleaved between the other threads flag set at the well.
So if I ran this code, what would happen?
Oh, just
Or live lock, right? Yeah. This will be an infinite loop. Why?
like these things.
What do we know about the semantics of atomic?
Everything that's in that block has to happen all at once with respect to an observer.
So atomic, atomicity, what's the second one? So what's the second property we talked about? Atomicity? Isolation. So what does isolation say? Yeah.
It says that we can't observe the rights.
We can't observe the right, so we will never see anything that comes out of this transaction before it commits. So, and the same for this transaction. Therefore, we're not going to get any forward progress with this code. Okay, so, this is a case where replacing synchronized with atomic won't work. What's wrong with this code? Yeah.
You don't know the order in which the three atomics will run, and so if like the pointer gets set to null after pointer set to A, then the last atomic will not be in it. Like where we say B.
So what might happen? I may dereference a non-pointer, right? And how would I fix it? Right. So we wanted to get rid of that, right? So this is known as an atomicity violation, right? So where you put atomic around the wrong set of code, and therefore your behavior, your atomicity behavior, is incorrect. Okay. So, all right. So any questions about the abstraction of transactional memory and sort of why it's useful? Okay, let's talk about the fun stuff, the implementation of transactional memory. How do we actually make this abstraction work? Okay? So, we got to talk about the three components of the abstraction: atomicity, all or nothing; isolation, which we just talked about; and serializability, right? And so these are the properties that an implementation of transactional memory has to provide, and it has to provide these things while giving you as much concurrency as possible, right? So that's the goal, right? And in thinking about a set of transactional memory implementations, there's a space. An implementation space that is defined by how you deal with the transactional memory state which is called data versioning. So how you deal with the uncommitted state that a transaction hasn't committed yet, and the committed state that a transaction that's previously committed has already updated. So that's the data versioning policy. And the second component of transactional memory implementation is how we detect conflicts. When and how we detect conflicts, and this is called the transaction conflict detection policy. So data versioning policy and conflict detection policy. So let's start by talking about data versioning. So this is how we manage the state that hasn't been committed yet by the transaction and the state that has already been committed by previously completed transactions, right? There are two ways of managing data. One is called eager versioning and requires the component of a undo log. And the second way is lazy versioning, where we have a write buffer as the key element in the system. So let's look at these two kinds of doing data versioning. First, eager versioning, right? It's called eager because you update memory as early as possible. Now, memory in this case could be the cache, right? And as we said, the key element of the eager versioning scheme is an undo log, because we need some way of undoing the data updates that we've made in an eager manner, right? So in this example, we're going to have a single variable x that we are updating in the transaction. And x initially has a value of 10 in memory. And the transaction is going to write 15 to x. And so what we do then is we put the old value of x into the undo log, right? So x value of 10 goes into the undo log, and we eagerly update memory. So memory becomes 15, right? So this is good because now memory is up to date, and that is always good, right? Now, what happens when we commit the transaction? What should we do? Yeah, throw away the undo log. We're done, right? Transaction's committed, memory's up to date, we're done. All right, what happens when we abort the transaction? Now we need to restore memory to the state before the transaction executed, right? And so now this becomes we need to apply the undo log to that, and we get memory back to its original state. Okay? Yeah.
Is this sort of more complex abstraction? Because we have to put the log somewhere.
Yeah. We're getting there. has all sorts of impacts on the implementation of what you do, and we're going to talk about both hardware and software ways of managing this, right? So we have this undo log, and we update memory, we restore memory to the state that it was before we started the execution of the transaction. Okay, so that's eager. Yeah, question?
When do transactions abort again? Is this like for an error or a conflict?
Well, you can abort for A. You just pull the abort cord, and you can bail out of a transaction whenever you want, right? And you know that none of the state of the memory is being changed. It's great, right? But the other reason that you might want to abort a transaction is because you detected a conflict, right? Yeah.
So you just do the transactions, and if there's a conflict, you undo and then do them later.
Well, there is the system has to determine when to. You will usually just restart the transaction, right? You try again. Yeah.
If the undo log is like a certain size, like it tells you how much money you can pay with it.
Yes, it depends where you keep the undo log, right? So you could have an explicit cache for the undo log, or you could have just put it in regular memory, and And depending on sort of whether you've got specific hardware mechanisms for handling it, or you just put it in memory, which would be the most scalable mechanism.
You put it in memory and you have a cache and make a separate.
Right. So you assume that there's locality in all your accesses, and caches work for memory that you access here too. Yeah.
Is it right to say that all the transactions start coincidentally and until the observer conflict, like they would commit, if the observer conflict, they would avoid one of the transactions?
So we're getting to conflict detection. So now we're just talking about how you manage data. The next topic will be how we detect conflicts and what we do. Yeah.
Just to confirm, in the undo log, are we only keeping the values in the memory before the threads are executing? We're not keeping like intermediate.
No. Remember, you need to get back to the state before the transaction started executing. So we only need to keep the first time you write to it. Any subsequent updates don't need to be put in the undo log, right? Yeah.
What happens if the undo log gets corrupted or somehow gets like something goes wrong with the undo log before the transaction is complete?
Well, then your system is corrupted, right?
So this would not be resistant to that kind of a crash.
Well, I mean, corrupted how, right? I mean, you need some other mechanism for dealing with memory fault tolerancy, right? If that was a problem, if it's a problem that you wanted to guard against. But let's assume for the sake of simplicity that our system is robust. All right, lazy versioning, right? So everybody likes to be lazy, right? And here we have a write buffer, right? And as the key mechanism. And so again, in this example, we're writing to X. So we, instead of updating memory directly, we write into the write buffer. And that's why it's called lazy. So now that we've done this, have we created some complexity to what happens to the rest of the reads to X in the transaction?
You have dependencies, don't you?
Well, you may have dependencies, clearly. And the question is, where should subsequent values of X come from? Memory? No. They have to come from the write buffer, right? Write buffer is the most recent value of any variable that has been written. And so now we potentially have to check in two places. So there is this extra complexity that occurs, depending on how it gets implemented. But it's something to keep in mind, right? That because we haven't eagerly updated memory, we now have two places potentially where data that we may have to look for the latest value of data, right? As opposed in the undo log, you never look in the undo log, right? You only use the undo log when you're trying to fix an aborted transaction. All right, so in the case of commit, we now have to update memory from the write buffer, and then, of course, clear the write buffer. What do we do in the case of abort? You just throw it away, right? We just throw away the write buffer. We don't need to. We haven't changed memory, so we're good. All right. Everybody understands the difference between being lazy and being eager? All right. So now let's talk about the trade-offs between the two, right? So in the case of eager versioning, we update memory directly, which is good. And we maintain this undo log, so we get faster commits, right? The data is already in memory, and we only have to look in one place. But the problem is that we have slower aborts, and because we've updated memory, managing fault tolerance is trickier, right? Because now we've got to figure out how to restore memory in ways that may not be completely obvious. Lazy versioning uses a write buffer. We potentially now have multiple places that we need to check. it gives you faster aborts because you just throw away the write buffer, but commits are slower because you now need to take the contents of the write buffer and apply that to memory. So that's data versioning. So now let's talk about conflict detection. Yeah, question.
Does the the eager versioning scheme make isolation harder if there's another thread also doing the transaction, which may have written in memory, in which the gets read?
Yes. The way that it potentially makes isolation trickier depending on how you do conflict detection, which we'll get to next. So typically, okay, well, we'll get to that, and it'll be clear as to what's going on. Yeah?
One quick question I had was when you have, let's say, eager commits, right? You're going to be accessing the memory very often, as opposed to, so the amount of memory utilization is higher, so that would be more conflicts in the buffer, right? Isn't that a consideration when you're making this decision?
So the key elements of how you kind of make the decision about what data versioning scheme to use have to do with the combination, really, of how you do conflict detection and how you do.
Go together.
Yeah, so they essentially go together. And so once we talk about conflict detection, then we can come back and revisit your question if it's not clear. All right. So conflict detection, right? So we need to detect conflicts, right? So either read-write conflicts or write-write conflicts, right? So essentially, you've got two transactions, A and B, that are either there's either a conflict because one transaction wrote address and another transaction read that address, or both transactions want to write the same address, right? So we've already talked about the concept of a read set and a write set in the context of that tree example. But to be explicit here now, read set are the addresses that have been read during the transaction, and write set are the addresses that have been written during the transaction, right? So, again, there are two schemes. There's pessimistic detection, or encounter detection is another name for it, where what you try and do is you try and detect, you assume that the transactions are going to conflict, and you want to find the conflict as soon as possible. That's why it's called pessimistic. Okay? So, and then the contention manager decides whether you should stall or abort the transaction. And we'll look at examples where we do both, right? So let's look at pessimistic in this case. So we in these diagrams, we're going to assume an aggressive contention manager that always allows the writer to win, and so other transactions have to abort. And in each case, we want to be able to look at the pessimistic detection policy. And so on every access, you need to do the check for conflict. Okay, so in this case, we have a read of A by transaction 0, right? So in this case, the read set of transaction 0 is A, right? And the write set of transaction 1 is empty, right? So the check says no conflict, right? So we keep going. And here, with this access, the write set of transaction 1 is B, and the read set of transaction 0 is still A, and the write set is empty. So again, no conflict, right? And then on right of C by transaction 0, now we have a read set of 0 is A, and the write set of 0 is C. And here we've got the write set of 1 is B. So again, we do the check and there's no conflict, and both transactions commit. Okay? That's the first case. All right. Second case. Let's get rid of the... All right. So in the second case, I've got a write of A, and I do a check. And then I do have a read of A on transaction 1, right? And so in this case, write set of A is, write set of 0 is A, and read set of 1 is also A. So this is a conflict, right? And so what are my options here? I could abort 1 and restart it, or I could assume that at some point the transaction 0 will complete, and I can then commence, so I can stall transaction 1. And what would be the benefit of stalling transaction 1 as opposed to aborting? Yeah.
You don't have to do the read of A again?
Yeah, all this work's done in transaction so far does not have to be flushed. I can just hold the state of transaction 1 until transaction 0 completes, and then I can resume transaction 1 until it completes. So this is an early detect and stall. Yeah?
But wouldn't that be an issue with A, which is not the fresh value?
Well, you got to read it again. Yeah.
So it would be after the stall, you go back and read.
You go back and read it again. Yeah, absolutely. You have to.
Yeah.
Yeah.
We might get this, but what if you had done maybe like a read of BMT1 before, and then that gets written to after you've stalled? So basically, like when you go to like, resume the T1, like you have multiple conflicts.
So you're saying that later transaction 0 wrote B?
Yeah, like T1 finds that later, like multiple things is read have been changed by T0 after it.
Well, so remember, every time you do an access, you're doing the check. Every time. So if there was not a conflict up to this point, you would not have stalled.
Right.
Now, if there was a later write by T0, then it would cause T1 to abort.
You'd abort. Okay.
Yeah.
How do you know that there's been a later write if you don't have save since you committed it? Like, do you check on like read on whether your current read states are similar to what's
Well, the system has to keep track of the read state and write state of all the transactions that are in execution.
Yeah, but like T0, let's say it's committed that transaction, right? Once it's committed that transaction, is it still sitting there? Like, is it still like? Is that
No, and then you're done, right? It's committed the state. It's committed its state.
Yeah.
It's updated the state of the system, and then every other transaction that's running will get the latest state that.
But like he said, like P1 is already read like B, which has been written somewhat later in P0, let's say.
Yeah, at that point, so every pessimistic detection says on every access, I do the check.
But how do you kind of do the check here?
No. So if the case is, suppose above here, I had read B, for example, okay? And then down here, I wrote B. At this point, this would cause this transaction to abort.
Oh, I see.
Right?
I see. So even though it's stalled, like you can
Even though it's stalled, yeah, the state's still around, right? And I'm still doing the checks, right? So the stall becomes an abort. Yeah. Any other questions? Some of this can get tricky. It's going to get slightly trickier, but not much more. All right. So in this case, we do an early detect. Instead of throwing away the work that we've executed in the transaction so far, we stall and hope for the best. And we wait for transaction 0 to commit, and then we can commence executing transaction 1. All right. So case 3, we're going to do a read of A. Read set of 0 is A. The read set and write set of transaction 1 is empty, so the check passes, right? And then we do a write of A on T1. So what happens in this case? Yeah. T0 aborts, as we just talked about. So it restarts, and then we do a read of A, and then we do a write of A. Okay. Okay. Read of A, stall, and then we keep going, right? Any questions? Yeah.
So when do you know that you start T0?
Remember, aggressive contention managed on writes, writer wins, so other transactions abort. So writer always wins. So at this point, if there's a conflict between a read-write conflict, the writer wins, right? So if you've already written and then you're doing if another transaction is already written and then you're doing a read, then you stall, okay? If you've read already, you've read bad stuff and computed based on that, and then a write comes along, then you have to abort. Remember, up until this point, you haven't done anything that would be a conflict, right? You're checking to see whether this read will cause a conflict. If it doesn't, you go ahead and do it. If it does, you just stall because you haven't done it yet. You're thinking about it, right? And then once the commit is done, then you go ahead and do the read because you know that the stall condition has been cleared. Yeah.
Oh, sorry. I was just noticed in case 3, it looks like we start T0's read A before T1 has committed. I guess I'm just wondering, when does that restart happen, or like how do you know that you can? Yeah, what restarts? What condition restarts?
Whenever, in this case, you abort and restart whenever you see a write-read conflict.
So you just restart immediately?
Yeah, exactly. Yeah. Okay. All right. Case 4. So now we have a write of A. So what happens? Does this check pass? Yep. We have a write of A on T1. Does this check pass? No. So what should happen? Abort and restart, right? and we have a write of A. So what should happen? Okay. Okay. So we're not going to make any progress, with this scheme. So the system has to detect this situation, right, and allow one of the transactions to complete. Okay, so you've got to, this is a live lock condition, and you need to detect it. All right, so this is pessimistic. Yeah, go.
Would you ever design a memory system that would give the reads precedence over the write? Like, so people cause the write thread to the work?
Let me think. So so you've already written. So this case, you want to cause T0 to abort in this case. Is this what you're?
Yeah.
I can't see why you want to do that. But possibly. But I've never seen a system that works that way. Yeah. Yeah.
What would be a different type of contention that would
Other than sort of allowing rights to. You could allow the read to you could allow the transaction that's already running to. I mean, you could abort the transaction that's doing the write, right? Instead of having the write do having the reading transaction be aborted.
It's like a first come, first serve.
Yeah, right. But yeah, there are many options for contention management, and different systems have been implemented with different advantages depending on sort of what the particular application scenario is. All right, so optimistic. I think in the last 5 minutes we can at least make a run on optimistic, right? So optimistic is, hey, I don't think there are any conflicts, therefore I'm only going to check when the transaction commits, right? Until that point, I'm going to assume that everything is hunky-dory and there are no conflicts, right? And so the nice thing about this is that you can always give precedence to the committing transaction. So the committing transaction will cause all other transactions to abort, right? So let's look at the example here. We're not doing any check. So pessimistic is I detect as I go. Optimistic is I need to check the write set of the committing transaction, which is B, against the read set of all other transactions. In this case, just 0, which is A and C. There's no conflict. So the detection says, the conflict detection says no problem, and the commit happens. Yeah. Is read set what?
With T0.
Sorry. You're right. So write set of 0 is C. Okay? So you're checking against the write set of the committing transaction versus the read set of the transaction that has been the other transactions in the system. Okay? I'll talk about the okay. So in this case, what happens? The write set of the committing transaction is A, and the read set of the other transaction in the system T1 is also A. So what has to happen? Right, you abort and restart, right? And so in this case, you don't get to stall, right? So you got to restart. You don't detect early that this is going to be. This is sometimes called a doomed transaction, right? Because you know at this point that this transaction will not succeed because there's already a write in the system that's going to cause a conflict, and therefore you waste all that work. In case 3, we have a read of A, and write and commit, right? So we read A. Of course, that read of A could happen anywhere in the transaction, right? It could have happened after the write of A here. It could be down here in time, right? Right? But it doesn't matter, right? So in this case, T0 is committing, and its write set is empty, right? So you're checking the write set of the committing transaction versus the read set of other transactions, right? And you say, go ahead, right? In some cases, and if I gave you an example, I would say explicitly, you might want to check to see whether the write set of the existing transaction conflicted, but it really doesn't matter because the serialization is such that the committing transaction is going to update the state of the memory, and even though there are other writes that exist, there will be no conflict, right? So in this case, we do the commit and of T0, and then we do the commit of T1. And in fact, the read of A, you serialize these transactions, the read of A happens before the write of A in the serialized transaction order. And so that means that, of course, transaction 0 should not see any of the updates of transaction 1. All right, so in this case, we have a read and write here, and what should happen? So the read set of T1 and the read set of T0 are both A, and the write set of T0 and the write set of T1 are both A. So what should happen here? Yeah. T0 should restart because we have a conflict between the committing transaction and the transaction that already exists. And then we restart, and then we go ahead and commit. And in this case, for the pessimistic detection, there was no forward progress. But here, with optimistic, you do get forward progress. Yeah?
So the write to A that T1 performs, right? That value might depend on the fact that T0 had written to A before, right?
Because T1 reads A after T0 writes to A. So doesn't that mean that when we abort T0 and restart, but T1 is already committed, like the values that T1 has committed are committed assuming that...
Remember, everything's isolated until the transaction commits. So there are no values being communicated between transactions until commit time. So any values that T1 and T0 are reading at this point existed before the transactions commenced, or were created inside the transaction themselves. Yeah.
With eager versioning, or writing it in memory? How do you...
Yeah, so eager versioning and optimistic detection don't go very well together. Yeah.
Why in case 3 do we not restart, but in case 4 we do? What's the difference there?
In this case? Remember, what's the rule for a committing transaction with optimistic detection? The write set of the committing transaction gets compared against the read sets of all the other transactions. What's the write set in the case of case 3? It's empty, right? There's no conflict.
But you don't compare the reader. You only do like one way. You don't do the other way.
No, it's the write set of the committing transaction. Okay, so I think time's up. So we'll pick this up again on Thursday, and we talk about software and hardware implementations, and we might move into discussion of application-specific or domain-specific hardware.